Okay, hello everyone. Um, so today this lecture is part one of a few lectures I was going to give on terrestrial planets. Okay, so remember how we kind of divide up the planetary region of the solar system, right? We have the terrestrial planets, the inner planets kind of close to the sun in our solar system. These planets are Mercury, Venus, Earth, and Mars. So your reading assignment kind of glosses over Mercury, but I do want to spend the first lecture in this series talking about this planet. But first, let's think about what defines a terrestrial planet. So this region is about the inner 3 AU, right, an astronomical unit of the solar system. These bodies are solid. They have rocky mantles and metallic cores. They also very probably have the same formation mechanism called coagulation, right? It's a gradual sticking together of smaller rocks called planetesimals until they become the large rocky bodies we know today. Because these planets were formed from smaller rocks colliding into each other, we think that during formation about 4.5 billion years ago, these planets were very hot, like molten even. That allows for a process called differentiation, right? The iron and nickel that the cores are made of, that was allowed to kind of fall to the center of the planet because they're heavier than the other rock that makes up the crusts and mantles of the terrestrial planets. Okay, so like I said, we are first going to talk about the planet Mercury. So Mercury is the smallest planet in the solar system. It has about a 4,800 kilometer diameter, which is only about 40% larger than the moon. So it's actually not even all that much bigger than the moon. Its distance varies between 77 million and 222 million kilometers from the sun. So it's actually relatively pretty close to the sun. Mercury has no moon, barely any atmosphere, and it experiences really extreme temperatures. So daytime temps can reach as high as like 800 degrees Fahrenheit. But without an atmosphere to hold all that heat in, nighttime temperatures can get really bitterly cold and dip as low as about negative 290 degrees Fahrenheit. Mercury is actually not the hottest planet, though. That goes to Venus, which we'll talk about later, with its thick carbon dioxide atmosphere. So Mercury's thin, barely there atmosphere is called an exosphere, and it's actually made up of atoms blasted off the surface by the solar wind and striking meteorites, and is composed of mostly oxygen, sodium, hydrogen, helium, and potassium. Don't let the presence of oxygen fool you. It's way, way too thin to actually be something breathable. Um, but yeah, it's really thin. There's just not enough there to hold in any of the sun's heat. So nighttime gets really, really cold. So Mercury is really small and it's really close to the sun. So here we have the moon and Venus, and right here, very faint. This is Mercury. Because it's so small and it gets really overwhelmed by the light of the sun, it's not one of the most impressive planets that we can see from the sky. The light from the sun really does drown it out, but it is visible enough to act as like a really important test for general relativity, kind of back in the day when we were still trying to figure out if this was something we needed to pay attention to or not. Okay, so according to Kepler's first law of planetary motion, remember, all planets orbit the sun in an ellipse, and the sun is at one of the foci. Um, because the orbit is an oval and not a perfect circle, there is a point when the planet will be closer to the sun than at any other time. And remember, this is called perihelion. So before Einstein published his theory of relativity, physics, really kind of operated under Newtonian mechanics, right? So basically how things look in our normal life, right? We talked about Newton extensively. But under Newtonian mechanics, where perihelion happens in an orbit shouldn't change. But in fact, it does change, and it changes mostly by the tug of other planets in the solar system. So this is one of those things that can make really kind of super precise orbital calculations a little bit tricky. The solar system, right, it isn't empty, right? In fact, we have Jupiter and to a lesser extent Saturn out there being really humongous, tugging on these smaller guys in the inner solar system. So what results is this precession. You may have heard the term before with regards to Earth's rotation on its axis. I believe we talked about it in an earlier lecture. So over time, it makes a little circle, right? So here's just an image of how Earth's axis will precess, make a little circle over time, kind of an exaggerated diagram. So this is what's happening with perihelion as well. The perihelion will rotate around the center of mass, and this is kind of what it looks like. So every planet's perihelion precesses, um, but 100 years ago, it was really hard to get accurate measurements of any planet's perihelion precession except for Mercury, and something wasn't right. So the amount of precession predicted by Newtonian physics didn't match what was measured. The precession was off by 43 arc seconds per century, so a really, really tiny amount. This amounts to a little more than 1/100th of a degree per every 100 years. So really, really small, but measurable. Um, so if we want to say we understand the solar system, even though this is small, this is something we have to kind of figure out, like why, what is causing this? And so this is really what it looks like over time. You have the GIF here of a planet going around a star, and the location of its closest approach, it changes just a little bit. It kind of makes this curly Q shape. For a while, some people thought that there was actually another planet between Mercury and the Sun. I mean, no such planet was found because no such planet exists, right? So there has to be another explanation. General Relativity was published in 1915, and it was able to predict the perihelion precession of Mercury perfectly. Because Newtonian physics isn't exactly wrong, it's just incomplete. It describes everyday life really well, but general relativity is a more complete theory and it requires just a small correction right here. You don't have to know that for any exam or anything, it's just for your own education. Just a little correction made to the gravitational force exerted by the sun. And it fully accounted for this 43 arc seconds per century discrepancy, and it's considered one of general relativity's first big wins. So Mercury was a pretty important little planet. More than that, Mercury has a kind of perplexing geologic history. There was a spacecraft called Messenger that operated several years ago that really revealed this. So Mercury formed about 4.5 billion years ago with all the other planets when gravity pulled swirling gas and dust together to form this small planet. So like its fellow terrestrial planets, we're pretty sure Mercury has a central core, a rocky mantle, and a solid crust. So this is kind of a cross-section of what we think Mercury looks like on the inside. Mercury is the second densest planet in the solar system after Earth. It has a very large metallic core with a radius of about 2,000 kilometers. So it's about 85% of the planet's radius, right? You can see this is the core and it's actually most of the planet, right? There is some evidence that it's at least partly molten or liquid. Mercury's outer shell, which is comparable to Earth's outer shell, like the mantle and the crust, is only about 400 kilometers thick. So scientists estimate that the planet's radius actually may have shrunk by as much as 4.4 miles or 7 kilometers since it formed, and it's probably still contracting today. The most obvious feature of Mercury are its impact craters. So these craters are named for artists, musicians, and authors. I think there's one even named for Dr. Seuss. Many of these craters probably date from not long after the planet formed, so really quite old craters. At the beginning of the solar system, there was a lot of debris flying around, and impacts were extremely common. So these craters are very large and have noticeable impact basins. So the largest of these is the Caloris Basin. It's 950 miles wide, so it's really, really wide. Many craters have these bright streaks emanating from them called crater rays. You noticed this when you did your moon observation assignment. You identified crater rays, and they're formed when an asteroid or a comet strikes the surface. The tremendous amount of energy that's released in such an impact really digs a big hole in the ground, and it also crushes a huge amount of rock under the point of impact. Some of this crushed material is thrown far from the crater and it falls to the surface, forming these rays. The fine particles of crushed rock are more reflective than large pieces, so these rays look brighter. Um, in a space environment, dust impacts and solar wind particles will cause these rays to darken over time, but the younger ones are pretty bright, as you can see. And as you know, they're not unique to Mercury. We see these on the moon, as you guys pointed out in your assignment. We also see these on Mars as well. Mercury isn't completely covered in craters. It also hosts some smooth terrain and cliffs that can be a mile high and hundreds of miles long. And these were likely formed as the interior of the planet cooled and contracted over the last few billion years. So this is kind of an elevation map of the planet. You can see there's some pretty high places as well as some pretty low basins. Mercury's geology is really as complex as any of the other terrestrial planets, but it's the craters that are kind of the locus of mystery. And this mystery envelops a lot of things that we just don't really understand about Mercury. So there are features on Mercury that have been dubbed hollows. And as far as we can tell, these are actually totally unique to Mercury. We've never seen anything like them anywhere else. So these hollows are unique sunken regions encircled by bright halos. So they were first noticed as bright splotches by Mariner 10, which is uh, a flyby we did, or a mission to Mercury that we did in the 70s, I believe. Um, and they have like an apparent volcanic nature as revealed by the messenger probe. So the problem with these hollows is that they shouldn't be there. Volcanoes, as we usually think of them, spew up rock, but they also spew up gas, and Mercury's interior gases should have disappeared long ago. These hollows, though, do not appear to be that old. And remember, Mercury doesn't have an atmosphere, no wind or flowing water. So these hollows couldn't have been formed by those mechanisms either. The hollows, like I said, are probably not very old, maybe around 100,000 years old, which, considering the entire planet is about 4.5 billion years old, that is not really very old at all. They're so young that it's actually conceivable that they're still evolving. The hollows have been imaged in detail, or the ones that have been imaged in detail lack any craters overlaying them. So they occurred after Mercury's major cratering eras. The hollows also appear almost exclusively in Mercury's darkest areas, blanketed by what scientists call low reflectance material, or LRM. So the thought is that something about the LRM regions must be favorable to hollow formation. LRM is high in magnesium and calcium and sulfur, so it may be that one or more of these elements are involved in creating hollows. LRM also has a greater abundance of carbon, probably in the form of graphite, so another substance that could be responsible for the creation of hollows. So while it's evident that the hollows form through some kind of sublimation, right? So when a solid turns directly into a vapor, that causes the kind of surface to sink down. The specific mechanism is really it's still a mystery. So there's a lot more I could say about Mercury's geologic history, but I don't want to speak for hours and hours on these terrestrial planets. So for right now, it will have to do to just say, so even though the planet looks a little bit boring at first blush, there is still a lot that we can learn about it. So that's it for the Mercury lecture. The next lecture will be on Venus.